So welcome everybody to the 991st monthly meeting of our amateur telescope maker in Boston. We have Professor Priyamvada Natarajan, who is the chair of Astronomy Department of Air, who is speaking to us today. So now, jumping forward. So we have a slight change in our meeting agenda. We will have the speaker speaking first and then followed by the business meeting. Now, according to our bylaws, we need to make sure that all the members agree to this change. Dr. Priyamvada was supposed to be here. She's not feeling too well, otherwise she would have been here with us. But she was kind enough to be still with us through Zoom. Thank you. So I would like to see of hands from the members that it is okay to proceed with this forum in this format. All right, great. I think we have a majority.
Just please don't get up and leave when Glenn and I get on.
Yes, so our business part.
The question here is going first. We don't mention the vote.
So our business part of the meeting is contains our observers report and treasurer's report and such, right? So I hope you will all stay to listen to the observers report and all the other. We have tried to keep things shorter than before. We have been having discussions on how to reformat it. So hopefully you will enjoy this new format. So now I'll just jump into the talk and I'll give a short introduction to Professor Priyamvada Natarajan. So tonight we are honored to welcome Professor Priyamvada Natarajan, one of the most influential theoretical astrophysicists of our time. Professor Natarajan is the chair of astronomy at Yale University, and her work spans some of the most profound questions in modern cosmology. Questions about dark matter, dark energy, the formation of the first structures in the universe, and the growth and evolution of black holes. Starting with the telescope, she was gifted at the age of 4. Her aspirations led to her to study at MIT and Cambridge University, and she has built a remarkable career pushing the boundaries of our understanding of the cosmos. Professor Natarajan is internationally recognized for her pioneering models that map dark matter using gravitational lensing and for developing theoretical frameworks that explain how supermassive black holes seed and grow across cosmic time. Her predictions have been repeatedly validated by observations from Hubble Space Telescope, Chandra, and now the James Webb Telescope, placing her at the forefront of connecting theory with the cutting-edge data. Beyond her scientific accomplishment, she is a gifted communicator. Her best-selling book, Mapping the Heavens, traces the evolution of our cosmic worldview, and she's one of the astronomy's most compelling public voices, bringing clarity, rigor, and imagination to some of the universe's most challenging mysteries. She has received numerous awards for research and science communication and has been elected to prestigious academies and international scientific boards. Professor Natarajan is also known for her leadership in encouraging diversity and inclusivity in science, mentoring the next generation of astronomers, and engaging broad communities from universities to global audiences to think deeply about the cosmos and the humanity's place within it. Please join me in welcoming Professor Priyamvada Natarajan, a visionary astrophysicist whose work continues to reshape our understanding of the dark and distant universe.
Thank you. I'm very sorry I couldn't be there. I felt kind of a little unwell and not feeling so great. But I'm so excited about the work, and I know you were looking forward to this talk. So I'm glad to have the opportunity to talk to you via Zoom. So I want to kind of give you a status report, if you will, of all the exciting findings, in particular with JWST and the instruments aboard JWST. And as telescope makers, I'm sure that you are all aware of how it is really the collision of ideas and instruments that pushes the boundaries of scientific discovery. And in case of JWST, it's the instruments that give us access to the most distant reaches of the universe, taking you right to the moment of the formation of the first stars, galaxies, and black holes that is so unique about the power of this particular telescope. And I want to start off, and I know that there are probably different levels and there are probably many of you for whom this might seem a little not needed, an introduction, but I wanted to give you a sense of how our cosmic view has shifted, in particular in the last 100 years, and then I will talk specifically to the kinds of accelerated understanding and revamping of our thinking that the James Webb and data from the James Webb, the Hubble, and these other and Chandra telescopes have really pushed us to. So as you all know, our cosmic view has been evolving, and perhaps the first major dramatic sort of tectonic shift happened in 1929. This is, of course, I'm talking post-Copernicus. I'm talking in the last 100 years. So this is when the astronomer Edwin Hubble discovered the expansion of the universe. He found that galaxies that were farther away from us appeared to be hurtling away at larger velocities. And so the only way to reconcile this was to understand that this denoted an expanding universe. And from then on, we have had the need for more complex models beyond analytic estimates, blackboard estimates, to the use of very sophisticated computation. So the story, as I'm going to tell you, of the growth of intellectual knowledge and the production of new knowledge in cosmology is very, very tied to instruments and computation and the techniques that have enabled us to see farther, see better, and see deeper. So of course, now our current, is jumping on to where we are. Not only do we know that our universe is expanding, but we also know that the expansion of the universe has been accelerating. And that discovery happened in 1998. And of course, in order to accelerate, you need to provide some kind of energy to a system, just as for a car, a gas-driven car, you have to press the gas pedal in order to give it some acceleration. In the universe, this entity, mysterious as it is, was deemed to be dark energy that was fueling the expansion, accelerating expansion of the universe. So we've made like enormous progress. So in 1919 to about 1950s, we really believed, that the Milky Way, we knew the Milky Way, we knew, we went beyond the solar system, we knew we were in a galaxy, we started to pick up many other galaxies, billions and billions of galaxies over the last decades. And then we have also been able to do an exquisite inventory of the constituents of the cosmos. So this pie chart shows you that the bulk of the contribution to the energy density of the universe is this thing, dark energy, which is propelling, which dominates today, and it propels the accelerating expansion. A very tiny sliver, about 5%, is the ordinary atoms that we are made of. Everything on the periodic table is in that small sliver. And everything else in the kind of overall matter budget that is shown in green here in this pie chart is actually dark matter. So we actually believe that it is some kind of gravitating matter, so some kind of particle likely formed in the very early universe. And that, as you can see, dominates over the atoms that you and I are made of, all the familiar atoms. So as you might notice, I have told you that we have an exquisite inventory. And we also now know how these three entities manifest in the universe, and in terms of providing data from observational data from which we have inferred this, but their true nature remains really unknown. And so notice in this compositional chart, black holes do not actually contribute any significant amount to the energy density. But as we will see, they were therefore believed to play a very marginal role in the universe. But it turns out that in the last 10 to 15 years, we've realized that they are critical to shaping, like dark matter and dark energy, the visible universe. Black holes are really, they are center stage in the formation and the growth of galaxies, all the stuff that we actually see in the universe. So what we also now know is an exquisite idea of the timeline, the clock of the universe. JWST has caused us to move things around a little bit, in particular when we believe that the first stars and the first structures started to assemble. JWST has pushed that back even further out than we had originally believed. We were looking at the nearby universe and we were making extrapolations to what JWST is likely to see. But the data themselves have pushed us beyond our sort of imagination, which has just been sort of absolutely fantastic to visit, to sort of be part of and be involved. So as you all know, the universe, we believe, started with hot, dense plasma during inflation. The size scale of the universe was hot, dense, and compact. There was a very rapid exponential expansion, the inflationary epoch, out of which eventually the universe became radiation dominated, then matter dominated, and then dark energy dominated today. And this transition from radiation domination to matter domination is the critical one, because that is when we start to form all the familiar matter, including dark matter. And the dark matter, it turns out, forms the scaffolding in which all galaxies form. And so, Hubble actually, what was momentous about his discovery, aside from the fact that the universe was unmoored and it was expanding, was the fact that we were not alone. The Andromeda Nebula, as it was called, was actually a distinct galaxy. It was a separate galaxy from the Milky Way. And today, we see that not only are we not alone, but the universe is teeming with galaxies. So this is supposedly on the right-hand side, you see an image of the Hubble Ultra Deep Field, which was supposed to be a field that was largely empty, no clusters of galaxies, no gigantic structures, where it was chosen to not be that. And this deep look has actually revealed that there are hundreds of thousands, if not a million galaxies in this field of view. And I just want to point out here, with all the buzz with big data, right? Astronomy has always been the sort of the original big data science. We've always gathered a lot more data, even from the glass plates, starting from the plates to film to CCDs. We've been gathering vast amounts of data looking at the night sky. And especially when storage technologies became better and we were able to store the data, we could actually go and revisit the night sky, and we had a compendium of huge amounts of data. So where we are at in terms of the state of the art in understanding how structure forms are computer simulations. And as you know, cosmology is a very peculiar science in the sense that you cannot do any controlled experiments. A supernova goes off in the night sky in a particular spot, that's what you have. You can't make it happen again the next day. Unlike, chemistry, where you can take two test tubes and mix those reagents an infinite number of times to see if you get the same outcome. And the other problem with our universe is we are sitting inside the universe and we are making measurements. So the perfect proxy for experiments have been numerical simulations. They are not quite the same as experiments, as I mentioned, because you don't actually have, you cannot do an infinite number of replications just because it's computationally very expensive. So you start out with a set of initial conditions, and we understand enough of the order in the universe, the laws, to be able to see how the first galaxies formed, what the first black holes do, when they form, what they do, how they impact the growth of structure. So what you see in the bottom is the assembly of a spiral galaxy, much like our own, the Milky Way. And what it shows you here is how the way a galaxy forms is from it's hierarchical. Small galaxies form first, then they merge, collide with each other, coalesce, and form bigger and bigger galaxies. So structure formation is really hierarchical. What you see there are gas flows, which is shown in the sort of greenish hue. You see stars forming in the yellowish stuff that you see. And in the upper panel here, you are seeing what accretion onto a black hole does in terms of the jets that are produced by the black hole, how that heats pockets of gas, and you see sort of this hot gas in red regions around the center of a galaxy. So these are all key elements that we now understand reasonably well. However, as I mentioned, we don't actually know what the nature of dark matter is. What is the particular particle, right? So today I want to spend quite a lot of time on black holes, partly because JWST has recently revolutionized our understanding of the properties of black holes, the abundance of black holes. There have been many, many surprises, so I want to share that. So when I first started writing my book and I started looking into the history of the word black hole, little did I know that the term had a connection. I was born in India. So it had a connection to Calcutta, India and Calcutta. And in fact, it was the name, the term itself was coined in 1756, where it was a prison where the local Nawab had imprisoned soldiers from the British East India Company. This is when they were trying to establish colonial rule in India. And it was called a black hole because this prison was so tight and so small that it was a place of no return. Isn't it remarkable that it really coincides with the properties that are ascribed to black holes now? So what is a black hole? So I'm going to offer you 3 different ways to think about a black hole. And these 3 different ways are used by us astrophysicists and physicists. Depending on the kind of problem we want to solve, one of those conceptualizations is more useful than the other. So what is a black hole? So if you can imagine the geometry of space, as you all know, Einstein's theory of general relativity tells you that there are actually 4 dimensions, 3 of space and 1 of time, that are needed to uniquely define any event that occurs in our cosmos. And the geometry of space-time, the other breakthrough that Einstein, in terms of insight, was this relationship between the geometry of space and matter. He was able to show that there's a very deep and profound interplay between the shape of space and matter. So the presence of matter causes the shape of space to change and to be deformed. And it's that deformation that in turn causes motion and engenders the force of gravity, right? So gravity is kind of this interplay. Newton told us how gravity functionally works and operates, but he didn't tell us its origin, and that's what Einstein did. So if there was no matter at all of space would be flat. The presence of any matter would create a divot in space-time, so like a puncture, a pothole in space-time. So depending on the mass that is sitting on space-time, the divot can be quite deep. So that is kind of pictorially shown here with the sun. Whereas if you had a neutron star, which actually is much more dense than the sun, compositionally, it causes a deeper divot, a deeper pothole. And by extension, what a black hole does is actually causes a puncture in space-time. So that's one way of thinking about it. You can think of black holes as punctures in space-time, sort of extreme distortions of space, right? So black holes are basically special places in the universe where the curvature of space is extreme. And there's another sort of thing that is hiding in this sort of extreme curvature, and that has to do with the singularity. And we believe that where you have this extreme curvature that ends in a singularity, which is a point basically where all our known laws of physics break down. So, I mean, black holes are fascinating because in many ways, they also represent the limits of our knowledge of space and time. Another way to think about black holes is to think of them as stellar corpses, as material objects, as astrophysical objects that are left behind when massive stars live their lives out, explode, and they leave behind a black hole. So they're sort of stellar corpses. And finally, another way to think about black holes that really brings home some of one of the most peculiar properties is the intensity of gravity around a black hole. So we can think of a black hole as a region of space from which not even light can escape. And as an analogy, I invite you to think about, the force of gravity on Earth and how to escape the force of gravity. You actually need to give rockets that are launched boosted. You need a rocket to be boosted with fuel, and the acceleration that you need to give it is about 11.3 kilometers per second. That's the kind of velocity with which you need to boost it out to escape the grip of Earth's gravity. So by extrapolation, if you imagine from Earth, you have this escape velocity. For a black hole, that escape velocity is actually the speed of light. And that's what we mean when we say not even light can actually escape a black hole. So what I'm showing you here is this beautiful visualization from NASA Goddard, made by one of my colleagues, Jeremy Schnittman. And this is showing you the hot plasma gas that is assembled like a disk around a black hole, that region that you see, which is marked by that circle. So we are seeing a face-on view, and then we are tilting and rotating to give you a full view of what the geometry of that disk looks like. So what you see circling around is hot gas, color-coded to show you that it's extremely hot, about 10 to the 7, 10 million Kelvin or so. And what you see as a clean boundary that appears in the center, that is the event horizon. So that is the event horizon is where the escape velocity is the speed of light. And once you cross that, any matter or light cannot make its way back out. So just to go over the three ways, I'll just quickly wanted to show you. So this is the strength of the pull of gravity, one way to think about a black hole. So this is the escape velocity. And these are the stellar corpses that tell you that the most massive stars that start out life at birth mass is about 8 to 10 times or more of the mass of our sun will inevitably end up as a black hole at the end of their life. And this is again sort of showing you a visualization of what I really meant when I said punctures in space-time. So this to kind of show you mathematically what the black hole solution is really the shape, the geometry of space around a point mass. And that point mass, a very compact mass, has an event horizon, a finite event horizon. And there are some very special regions around a black hole. So marked in the dashed line is the event horizon, the point of no escape. Whereas there is another region at around few times the event horizon, which is called sort of the light horizon, where light orbits are trapped and you are perpetually trapped around the black hole. And of course, if you graze past the black hole at much larger distances, then you will just be bent slightly, but you'll go on your merry way. You will not actually be swallowed up by the black hole. So this tells you a little bit about a mapping of the intensity of the gravitational force of a black hole as a function of distance from the singularity. So this is a graphic that, again, love very much. It was made by one of my colleagues at the Black Hole Initiative at Harvard when the Event Horizon Telescope project mapped the light that is swirling around just outside the event horizon, which is why we are able to see it. And this shows you the paths of light rays and how these images, you must have all seen that image of a donut. And this is showing you that red circle that you see there is the black hole. And you see in that grid, you see a puncture, you see a deep kind of distortion in the shape of space. If you see the grids, you can see it's stretched out quite a lot over there. So this is giving you a visual sense of how light rays get deflected around the black hole by its intense gravity. And these are the contributions to that big donut image that you saw. These are the various kinds of orbits coming from various distances that ultimately give you the picture that the Event Horizon Telescope, it was an incredible technical breakthrough, as you all know, where they managed to leverage the entire surface of the Earth as a single radio dish by choosing pre-existing radio dishes that were dotted around the Earth and synchronizing them. So the most compelling kind of evidence for the existence of a black hole, of course, comes from our own Milky Way's central black hole. Every galaxy, it appears, including our own seems to harbor a supermassive black hole, a black hole that is above 1 million solar masses. That's referred to as supermassive. And so this is beautiful data from Andrea Ghez' group in UCLA. This is work for which she was awarded the Nobel Prize in 2020. And what you see here is that star marks the location of the black hole. And what you are seeing is the full orbit of a star in the inner galactic region that is skirting. So it's obviously far enough away that it's not going to get swallowed by the black hole, but it behaves like a test particle that is just experiencing the gravity of the black hole. So what you see here is something like a solar system orbit, where in the case of the solar system, the pivot, the sort of the focus is where the sun is. So similarly, when orbits are mapped out, it actually tells you where the gravitating mass is. And the shape of this orbit tells you how much mass there is and how much mass is enclosed in that tiny region that is marked by the star. So it is so large that it cannot be anything but a black hole. So that was sort of incontroversial evidence. So that's a supermassive black hole. We know a lot more about their lighter cousins, the stellar mass black holes. So as you all know, the LIGO collaboration discovered the collisions of two stellar mass black holes that created a tremor in space-time. So they jittered the geometry of space-time, and those waves, called gravitational waves, were actually detected on Earth. So that first discovery was spectacular, and now it's just remarkable. We have several hundreds of those events. And so this is a very interesting diagram that in blue shows you the two masses from the gravitational wave, the wave pattern that you see. We can actually infer the masses of the two black holes that merged, as well as the final mass, all that of the merged black hole. So what we see here in blue are our current senses of stellar mass black holes. And the size of the blue circle gives you a sense of the mass. So we've been starting to detect a range of masses, which has just been spectacular. So, so we have these stellar mass black holes, we have the supermassive black holes, and obviously, if stellar mass black holes are the ones that grow to become supermassive, then they have to be an intermediate stage. They are, of course, unimaginatively referred to as intermediate mass black holes. We are yet to find them, and I'll talk about them a little bit towards the end of the talk. So some of the key properties of black holes are that they appear to be in one of two states. So they're either fasting or they're feasting. So any gas or stars that approaches the vicinity of a black hole close to the event horizon will get captured by the black hole. And that's how a black hole will grow. A black hole grows by gobbling gas that might settle in the centers of galaxies into sort of a disky geometry, because gas has angular momentum, it has spin, so it'll come and get pulled by the gravity and would form a disk around this very, very compact object. So when the black hole is actively feeding from the disk, you see it bright, extremely bright, because a small portion of the rest mass energy that gets pulled into the black hole is converted into radiation. And that radiation comes out in all manner of wavelengths, all the way from the UV to X-ray to gamma rays. And that is seen, and these objects, when they're actively feeding black holes, are referred to as quasars. And quasars are like the lighthouses in the universe. They're cosmic lighthouses. They are so bright that they often outshine the galaxy they're sitting in. And so they are detectable as beacons out to the earliest epochs of the universe. And JWST was going to find and has found some of the earliest quasars, the earliest accreting growing black holes. The other state that we find supermassive black holes in is fasting. Like the black hole in the center of the Milky Way is no longer growing. It has sort of tapped out. There's not very much gas left. So it's just sort of sitting there. And it just acts as if you will, a source of gravity that could just grab. If a star happens to stray past, it could pull and disrupt the star. That's the way things could light up in the center of our galaxy. Otherwise, it isn't really all that lit up. And so you may then ask, where exactly do supermassive black holes reside in galaxies? They are almost right at the center. We started out from a real Hubble Space Telescope image. We are zooming in, and of course, we don't have the resolution. This is an artist's rendition of what the accretion disk, this gas disk that I mentioned, looks like, that powers the black hole. And not all the matter that is in the disk actually feeds into the black hole. A small fraction of it, actually could be a large fraction in some instances, gets channeled out and funneled out as a jet. And so those jets are actually seen too. And this is something that I really like, and I thought you might all enjoy given your interest in instrumentation. So this is like a multi-wavelength picture of the Milky Way that's been put together, parlaying various kinds of instruments, telescopes that operate across wavelengths from the optical, UV, IR, X-ray, gamma ray, and radio. So it's just really, really spectacular. Just to give you a sense of scale, it's going to end up with the radio image of the EHD donut. And what you saw as sort of spiraling things coming out of the earlier images were actually magnetic field lines. And we know that magnetic fields threading the black hole do exist, and they're very, very important in moving energy between different forms. So some of the other intriguing properties of black holes is that there appears to be a correlation between the mass of the black hole and properties of the galaxy that is hosting them. So the mass in stars, the brightness of the stars seems to be correlated. So bigger galaxies host bigger black holes. And so this has been a challenge for theorists like me trying to see ab initio. Is there something about from the formation to the growth of a black hole? Are there ways to explain what is the origin of this correlation, right? Is there some causation behind it, or is it just a mere correlation? So this has been a very active field of work, and I want to show you a little movie from one of my former graduate students who's now a postdoc at Harvard. This is, black holes starting their life. These are the seed black holes that you see in red. They are growing. As they grow over cosmic time, what you see there as redshift Z equals is a clock. And as time goes on, and what you see in the plot are the measurements with error bars of that correlation that are seen today in the nearby universe. So this is just to visually show you that we can build models that over cosmic time start all the way from formation to growth and land up on the kind of correlations, giving you, going through fasting stages, ending up and feasting stages, and ending up today fasting as we see them. So we have a reasonably good understanding of how these correlations have come to be. So there are various versions of these correlations that just allowing you to sort of get a peek into. These are the various correlations. One is with the velocity dispersion, or the if you will, the gravitational pull of the galaxy that's hosting them. The other is the brightness of the inner part of the galaxy that is hosting the black hole. These correlations, we know of the existence of physical laws that order all these astrophysical processes. And so we are able to kind of discriminate between causation and correlation when we look at a particular process, like the formation processes. So there are particular ways of forming black holes that already natively give you this correlation to start with. So we'll come to that in a little bit. So this is just, this is spectacular image, and of both the donut in the imaged from the black hole at the center, the ultramassive black hole, 6 billion times the mass of the sun, and M87, and in the center of our galaxy, which is 4 million times the mass of the sun. So as I said, black holes have really moved to playing a starring role. We are seeing all kinds of phenomena associated with black holes across wavelengths. So these are some examples of jets that this is from real data. And, the question is, right around a black hole, because the jets from a black hole can heat the gas, they can actually prevent star formation. But it turns out there are various kinds of beasts. There are cases like this is an anomaly where the presence of a black hole is catalyzing star formation. So they play a real range of important roles in modulating star formation in galaxies. And how black holes actually feed. So this is from a supercomputer simulation. You are seeing a view. This is a cross section of the accretion disk, and the black hole is at the center there, and you're seeing the gas at various temperatures that is going to slowly siphon into the center. The other way black holes grow, aside from taking matter in from the accretion disk, is from collisions with other galaxies that are hosting other black holes. So the galaxies merge, their stars merge, some stars get spilt out, and then the black holes actually eventually merge. And when these two supermassive black holes merge, you expect gravitational waves, much like LIGO discovered for stellar mass black holes. For the supermassive black holes, they are at a much lower frequency than LIGO, and this can only be detected with the detectors in space, not on Earth. And the European Space Agency is shepherding a project called LISA, which is going to fly in the 2030s and should be able to start finding these supermassive black hole mergers that are occurring when galaxies collide. So that is really kind of the frontier. Just want to show you one of my own old simulations. It's an oldie but a goldie that has held firm and remained relevant. So this is what you see is the profile of the accretion disk in yellow around a black hole. This is a top view. You have a very massive black hole and you have a second one spiraling in during that merger process. This is the final stage of that merger we just saw with the galaxies crashing in. I'm zooming right into the heart of the final product, and you see how the secondary black hole that has come from a galaxy that has collided with another one is slowly making its way. And not only is it slowly making its way, but you can see the radiation, the accretion disk lights up. So you should be able to see some fireworks before the gravitational waves get produced. And that's what's exciting about supermassive black holes, that you will have these multi-wavelength observations that accompany two supermassive black holes merging. So these calculations are computationally have been incredibly challenging. And about 10 years ago, there was a major breakthrough. In the final stage, you need to take into account the shape of space, the detailed distortions and the shape of space. As long as the distances are large enough, general relativistic effects are not that important. But when they get close enough and you start getting to a level of few hundred times the horizon, you need general relativity effects to be taken into account. And they are taken into account in these simulations that I'm just showing you. So where do black holes form in our universe? So that's been a question that I have been thinking about since my PhD days in Cambridge. And this is a simulation of structure formation. It looks like nothing's happening, but actually there is dark matter, which is this blue haze that you see that is gravitationally aggregating, and it is forming structures. And it is the scaffolding on which ordinary matter, basically hydrogen gas, is going to fall in because of gravity and is going to condense. The dark matter, we believe, is made of a peculiar particle that doesn't actually collide. It's a collision-less particle. Whereas gas will collide because gas has pressure, it will collide, it will condense, it can cool, and it will form stars. So that is sort of the sequence of how we believe the first stars and the first galaxies would form. And of course, in there, somehow the first black holes have to form too. So conventionally, it was believed that the first stars that would form and leave behind a stellar corpse, those would be the only way to make the black holes, the first black holes in the universe. Of course, every subsequent generation of stars would also yield black holes. But the first black holes were expected to form only via that pathway. And my thesis advisor, Martin Rees, suggested, sort of speculated that there may be multiple pathways maybe to form black holes. It was unclear when he kind of suggested them in the 1970s, whether it was even feasible physics-wise, and of course, whether it happens in our universe. So one of the key sort of my preoccupations and obsessions was trying to see if there was any other way other than stellar corpses to make the first black holes. And yes, so in 2005 and 6, with one of my postdocs, we wrote a set of papers where we showed that this process called direct collapse, where you can form a black hole bypassing the formation of a star, just completely collapse the gas that you have a dark matter over density gravitationally attracting gas. The gas has some angular momentum. It will assemble in a disk. This is before any stars have formed. And some instabilities in the disk that can routinely happen will immediately lead to the funneling, much like the vortex of water that you get when you lift the plug in a bathtub, can very rapidly funnel matter into a tiny region and hence form a black hole seed by direct collapse. And so what is exciting about this kind of picture is that we were able to develop a set of unique observational predictions that you could directly confront with James Webb data and test whether such a thing can happen in our universe and how frequently if that may happen. So here is a very nice schematic of that process of direct collapse where you bypass the formation of a star. So what this requires, stars form, as I mentioned, when gas collapses, fragments, and cools to form a star. It has to be very, very dense to form. To ignite fusion, you need to go to very high densities. And we want to bypass that in the direct collapse black hole formation channel, and you can do that. We were able to show that in our universe, there exist not only the conditions, but the actual spatial locations where such direct collapse can happen. So one kind of scenario that allowed us to kind of close the arc, go from the basic physics, the conceptual model, to a real model, to a computational model, to one that from which we could extract observational predictions and then confront directly with the data, is a setting like this. So you have a galaxy that has actually formed a first set of stars. And since galaxy formation is hierarchical, such a galaxy would have a lot of little satellites that also form around it. Those satellites would not have formed stars yet. And the irradiation from stars that form in the parent will prevent cooling of gas and therefore enable direct collapse. So this little satellite halo would be the site where a direct collapse black hole would form. But then because it's a satellite, it would rapidly merge with the parent. And it will produce a weird kind of galaxy transiently, one in which the mass of the black hole exceeds or is comparable to that of the stars. And the light that is going to be emitted by such a galaxy would be dominated by the light that comes out of the accretion onto the black hole rather than just the stellar light. So those are two very unique sets of properties for this object. And by contrast, if you form black holes from stellar corpses, the same galaxy at that time would have a black hole mass that is tiny compared to the mass of the stars. So the spectrum that you get would be fundamentally different in these two cases. So we were able to predict the specific spectra in 2017, well before James Webb flew. I know this was a time when it was unclear. You may all remember James Webb was one day it was canceled, then it was back. It was sort of fighting for its life for a few years. But sort of we went ahead and made these predictions and was very excited at the prospects. And I'd like to think that this bolstered the science case, like our work really bolstered the science case. And one key prediction of direct collapse black hole formation is that object, that transient object, which we unimaginatively called overmassive black hole galaxy, would actually have to be detected not just in the James Webb Space Telescope images, but simultaneously in Chandra as well, because the flux, the emission would be dominated by accretion onto the black hole, a large portion of which comes out in the X-ray. So it has to be simultaneously detectable. That was a key prediction. And then, of course, we made spectral predictions. Just flash some. I know it looks a little busy, but what this just want to show you that we made sort of concrete predictions. The cooler colors and the orange and the red that you see are the spectra. They're pretty flat from about 1 micron to about 15 microns. And these are, and what you see in black are the detectability limits for MIRI, the infrared instrument on a JWST. So they all would be popping up. They are well above the limit, so they should be detectable. That's what we predicted. This is just to show you the dependence. The two curves, the two sets of cooler and warmer colors had to do with the spectrum of the direct collapse black hole and the little stellar component that is there. It's not actually dominant, it is subdominant, but its metallicity matters. The metallicity of the stars matters. This is just to show you the quantities that really matter. So we were able to make these concrete set of predictions, and then, of course, the universe gave us a gift. And I really could not believe when my collaborator, X-ray collaborators, expert in X-ray data, Akosh Bogdan, who's actually at the CFA, we had put in a proposal for Chandra to look at one of the fields that James Webb was going to look through. And for me personally, it was a super exciting moment because I work on mapping dark matter using gravitational lensing, and in particular, these regions that serve as nature's telescopes, where there's a large amount of dark matter, which kind of focuses the light from distant objects, behaves like a magnifying glass, and literally brings into view tiny wimpy galaxies and black holes, growing black holes that you otherwise would never be able to see with any telescope on Earth that we could ever build. So one such object that was simultaneously detected in Chandra and with James Webb was found, and its properties, and I'll show you in a minute, we had predicted such an object. If it had come from a heavy seed from a direct collapse black hole, it had to satisfy 6 properties. And this object satisfied all of them. And it was in place 470 million years after the Big Bang, pretty damn early. And it's a few times 10 to the 7 solar masses. So it's a supermassive black hole already in place with its host galaxy extremely early in the universe. So that kind of, as I said, the clock of when action starts in the universe got pushed, and this object was one of the key things that helped push the clock back. What other things JWST has been showing us is that it's opening an entire new window into black holes. So what you see here in this plot is the luminosity of the accreting black holes, and as a function of redshift or distance or time. And all the filled symbols that you are seeing are the black holes that have been discovered, the quasars discovered by JWST. Completely an area that was completely inaccessible to us from the ground. The gray stuff you see there is ground-based quasars that were detected, the accreting black holes. So this is opening up an entire new landscape, new portion of the parameter space. And so let me come back to this object UHZ1. That was, as I said, when the universe was about 450 million years. And so this is the sequence. This is why this alternate way of making the first black holes is really important, because it fits into the story of black hole growth and galaxy growth that we now know before JWST as well. And so what's intriguing is if you start out, the traditional seed is the light seed. It's the stellar corpse that has to grow a lot before it becomes a supermassive black hole. And if you have a direct collapse seed, it can already start life at 10,000 times the mass of the sun. Therefore, it doesn't have to grow too much, which means in the early universe, when you don't have as much time, you have a time crunch because you're seeing these already assembled supermassive black holes so early on that you need this head start growth to explain the properties. So this is once again showing you the spectrum of UHZ1, this direct collapse black hole candidate. In the data are the blue dots with the arrow bars, and the red is our model predicted spectrum. And it's just really remarkable. And these are all the quantities that we predicted. And these were published, as I told you, in 2017. So it wasn't, it was well before these objects were actually found. And we were able to show very compellingly that this is most likely one of the first direct collapse black hole formation. The seed for this source likely formed that way. So we are able to predict, for example, the ratio of the flux in the infrared to the X-ray. We're able to predict the track on which such an object should be. It should be X-ray dominated, and of course the infrared spectrum, as well as kind of the growth curves. So we're able to kind of explain how it came to be with the known physics without having to push too much. What has been super exciting for me, I'm going to wrap up shortly, is that I had also predicted other ways to form, even other alternate ways to form the first black holes. And this is when a nuclear star cluster forms in the early universe, that nuclear star cluster could incubate the formation of a black hole seed. And that has very special properties because it's embedded in a nuclear star cluster, which is very faint. So such a rapidly growing black hole might appear to have no stars associated with it. And thus, such candidates have also been found that ratify our prediction. So this is work that we did in 2014 in a paper that was published in Science. So basically, the conclusion is that nature seems to make black holes in multiple ways. And as I said, the frontier now is really LISA. This is an interferometer in space that should be able to detect gravitational waves from merging supermassive black holes anywhere in the cosmos. So I think, this is really what will be another sort of the next kind of game changer in the field. Theoretically, meanwhile, there have been some very interesting, somewhat speculative, but exciting old ideas that have had a second coming. And one of them is an idea by Stephen Hawking and Carr. They wrote a set of papers in the 70s of primordial black holes. While these are black holes, little tiny black holes that could have been created during inflation itself. So these would have been pockmarks in space, the geometry of space-time that were embedded during inflation, that kind of sat around, did nothing, but were just these weird regions, pockmarks in space-time, that eventually, when the universe got to be matter dominated, would then start to pull in matter and start growing. So this is a sort of an interesting speculative idea we've explored. Me and our groups and my research group and many other groups around the world have started looking at the possibilities of how to discriminate this scenario, for example. So the other kind of theoretical kind of frontiers, one other one is the understanding that you could have a large population of wandering black holes in galaxies, because not every merger would have completed to actual collision and coalescence. So you could have a lot of ongoing in-spiraling, because galaxies assemble through multiple mergers over cosmic time. You could have a ton of wandering black holes that are hanging around. And I think, there are some very peculiar James Webb objects that look like they could be candidates for that. So I will just wrap up here and open up for some questions. And if you want to know more, as was mentioned, I have this book that I wrote in which I talk about the history of idea of black holes, some of their key properties, and all the open questions. And I also wrote an article for Scientific American that many of you might enjoy reading. This is, of course, pre-JWST. So I'll just stop here and take questions. Thank you very much for your attention.
Yeah. Questions?
I have a question.
Yep.
Go ahead.
So looking forward, what is it that you plan to spend the bulk of your energy on in studying in the black hole arena?
So I think a couple of different things. So actually, we just put out a paper that we submitted to Nature 2 days ago. And that is leveraging, so there are these the way dark energy was found is that we know supernovae explosions are these standard candles. They are like standard light bulbs. And so their brightness is well understood, their intrinsic brightness. So the apparent brightness tells you something about the distance that they're at, as well as the intervening geometry of space-time. So these supernovae were instrumental in the discovery of dark energy. They allow you to map out the geometry of space-time. So I have long wondered how to connect my various interests, dark matter, dark energy, and black holes. With the U8Z1, I was able to connect black holes and dark matter because you needed that gravitational lensing. So this work, we were able to use accreting black holes, properties of some variable accreting black holes, standardize them as candles, and then use that to say something about dark energy. So for me, that's the new avenue that I want to continue to explore. So there are lots of large collaborations, big teams of hundreds of scientists who are trying to map out dark energy. And here we were able to show that as an alternate probe, this is a completely new way. And this is a small group of 3 of us who were able to kind of leverage the power of this new method. And so I'm hoping to spend time on that. And of course, also push on theoretically and conceptually on other new ways. And I published a first paper, sort of first calculation of another intriguing kind of possibility, led by this brilliant postdoc at NYU that I've worked with, where earlier in the universe, before, so the big open question has been, do stars form first or black holes form first, right? Obviously, if the only way for black holes to form is from stellar corpses, then the question is answered, that stars form first and then black holes come. But now direct collapse black holes could form before stars form. And so I've been looking at scenarios and seeing what kinds of predictions. The thing I love doing is sort of, building these conceptual models, sort of physics-driven, sort of new scenarios, novel kind of environments where you can have cosmic phenomena happen, and then connecting them to, making predictions that can be falsified or validated. So I think I'm going to continue in that vein, especially bolstered right now with the success of this particular class sets of predictions.
Thank you.
Thank you.
Any other questions?
I have a
I'll
question.
give you mic if you.
This is Carrie. May I ask a question?
Yes, please.
Dr. Natarajan, thank you so much for your talk. Really fascinating. I'm curious to know if you believe that black hole formation is necessarily tied to matter, and also whether the ratio of so-called normal matter to dark matter is changing over time.
Yeah, those are great questions. I think that if you look at the center of a galaxy and which is where the supermassive black holes are forming, growing, and so on, the density of normal matter vastly exceeds that of dark matter. So when you think about what the black hole could be feeding, what the feeding rate could be, what the reservoir of mass could be, you have a lot more normal matter that a black hole will swallow and grow rather than dark matter. So it's about a millionth to 10 to the minus 6 to 10 to the minus 7 at most of a supermassive black hole could have formed by dark matter falling in. The other reason is that dark matter, we believe, as I mentioned, the particle has these weird properties, which also limits the inflow rate, the accretion rate of dark matter. They are sort of collision-less particles that kind of just aggregate loosely through gravity. They do get fairly compact, but they never get as compact and as dense as normal matter. As for the question of whether omega matter might change with time, we do not believe so. The reason is all the ordinary matter in the universe, much of the 97 to 98% of all the matter in the universe, the ordinary matter, formed in the first 3 minutes after the Big Bang. So the bulk of the universe is hydrogen and helium. Everything else is a slight perturbation. Everything else, including everything that we are made of, all the metals, everything. And so everything up to lithium was made within all the lithium budget in the entire universe. Hydrogen and helium was made in the first 3 minutes. The bulk is, of course, hydrogen and helium. And whether the dark matter content itself can change, as I said, with this collisionless, non-interacting dark matter, not really. But if this dark matter was actually not collisionless and had some kind of self-interaction beyond gravity, then it's possible that, there could be some change and evolution over time. But that's a great question, because that's kind of a research paper question that we are sort of dealing with right now. So, and I promise you, this was not a plant. I don't know Kerry, so. I just saw a question flash by, which on the chat, and I think it was about the recent, that early galaxies. Well, I don't know exactly which result is being referred to here, but what we don't really know a lot about the origin and the sustenance of spins of galaxies. What we do know is that there is angular momentum, and that we know that whenever two galaxies merge, that angular momentum is going to get randomized, because they could have different angular momenta, they merge, and they get randomized. Whereas if a galaxy grows, doesn't merge much, then its spin could remain intact, or it could slowly spin up or spin down. So I think we don't yet have a full set of predictions, concrete predictions for what the spin distribution should be. The reason it may not be 50% at any epoch is because there are epochs in the universe where mergers were very, very frequent, especially early in the universe, when the universe size scale was smaller than it is today, where today, because of the expansion, the size scale of the universe is much, much larger. The probability of any two galaxies hitting each other, merging, coming close enough to merge, is actually kind of low. Whereas in the early universe, it was extremely high, the merger rate. And since mergers tend to randomize spins, the angular momenta, it's possible that there's a variation across epoch in what direction things are spinning.
Questions? You see gravitational lensing both from dark matter and from black holes, right?
Yes.
You can distinctly differentiate both?
Well, you need high resolution to pick out and separate out the effect of lensing just by the black hole. Because remember, the black hole, it's so compact that you first of all need things to line up exquisitely for gravitational lensing. So you don't actually, you are not often able to isolate the impact of just the black hole. You are able to see the lensing in a cylinder of the inner region of a galaxy, matter in that cylinder, which includes the black hole. So we are able to see that. I think in the radio, we will be able to, especially with NGVLA, the planned upgrade for the VLA, we should be able to start seeing, for example, the sort of the demagnified image that is expected in lensing. So you find a total odd number of images. You might have seen in Hubble Space Telescope images, sort of this arc and counter arc. In fact, there is one more image that is produced, which is in the center, that is demagnified. And you tend not to see it because there's a bright galaxy. Stars are sitting out there and it's hard to subtract them. But with radio data, with extremely high resolution, we may be able to see that middle image, and that properties of that middle image will contain information about whether there's a black hole or not.
Any other questions? Well, I have one more question then. Is the theory of the Milli charge taking any relevance into the black the dark matter having some form of a charge, which is milli charge, if I'm right?
Yeah, milli charged. Yeah, so that's one of the many kind of phenomenological models that has been suggested. So milli charged dark matter basically, as I said, offers a way of giving self interactions to dark matter particles so that they can actually interact with each other beyond just gravity, so that they can aggregate and they can actually create energy by annihilation or some kind of self-interaction and decays and so on and so forth. But it's one of many sort of speculative models. I wouldn't say it is even at the stage where it can even be compared with data at the moment. It's very much at the stage of phenomenological model.
If no more questions, anyone? Here. Okay, there is one question here.
The regular matter was made in the first three moments of the universe. And one of your questions was, is the proportion of dark matter to regular matter changing? And you said that the dark matter is non-interactive. And you didn't see it diminishing or changing in proportion. But if the regular matter is disappearing into black holes, is the proportion of regular matter in the universe diminishing?
Yeah, the proportion of matter that is disappearing into black holes is really minuscule in that inventory. So we don't really have the accuracy to track the fluctuations in matter at those very, very tiny, tiny percentages. Yeah.
Right, any more questions? Otherwise, we can wrap up.
Thank you.
Thank you.
Yeah, thank you very much. Thanks.
Thank you.
I'm sorry I couldn't be there in person. Yeah.
Thank you so much. Yeah, I know that you even have a fever, right? And you still
Yeah.
call. Thank you so much. Appreciate it.
Yeah. Thank you.
Want to share?
All right, so we will go to the next part of the meeting, which is our business meeting. Right. Rich and Glenn.
I'm glad to see everybody still here. This is awesome. And I hate to break it tomorrow. There is a little something about the moon in this presentation. Sorry. So we have the next slide. That'd be awesome. We'll just jump right into this. Now I think I can power through it. I'll use my teaching voice. So I think the first slide has to do with planet roundup. Then can you control that, or I'm far away from it? So I don't know if you've been looking to the southeast in the morning just before the sun comes up, but Mercury is actually putting on a pretty nice show. I've been watching it on these very cold fall mornings through windows in my house that face to the east. It's fairly bright. It's not minus. This is for today. Minus 0.5, 16 degrees above the southeast horizon. Elongation was just a few days ago. So you get a chance if it's not too cold, if you've got a nice view to the southeast. Get out there at about 6-ish when the sky is still relatively dark and see if you can pick up Mercury. Mars is lost in the glare of the sun. Venus, be really careful if you go out there and play around with Venus. It is preceding the sun, still at magnitude minus 3.9, but it's only 6 degrees away from the disk of the sun. That's getting into some pretty dangerous territory. It can be done. You just have to be really careful. If you are too afraid that the sun will drift in your field of view, wait another month or so and get Venus after it's past superior conjunction. And then it will be following the sun. It's a much easier observation. And superior conjunction is in a few weeks, on the 6th of January. All right, next slide. If you've been out looking at Saturn, you know the rings are still razor thin. We did a star party up in Arlington the other night, and the rings were like little toothpicks sticking out of the disk of the planet. Really pretty to look at. The ring tilt's only about a half degree. It's past its minimum, and from here on out, if you want to see it this thin again, you have to wait till about 2038 to pull that off. but it's still well placed in the evening sky. Get out there and look at it while you can. All right, next slide. Neptune is currently 4 degrees away from Saturn. It's about -8th magnitude. Triton is getting a little fainter. We're past opposition, so it's at magnitude 13.8. If you've never seen Neptune, you should try and go out there and find it. It's reasonably bright. I like to use 80mm finerscopes on my telescopes if I can, and so I can actually see that 7.9th magnitude star in the telescope. At the Arlington Star Party, we showed off Neptune, and what really gave it away was its bluish green color. Really tiny little disc, but the color is a dead giveaway for it. The kids, these were Brownie Scouts, and they were very happy to see Neptune. I tell people it's the least impressive thing you'll see all night through the telescopes, but ask all your friends if they've ever seen Neptune, and they'll tell you no. So there you go. So Uranus is a little bit easier. It's brighter, still near the Pleiades. We showed that the other night. Not as blue as Neptune, but it's got a distinctive disk because it's almost 4 arc seconds across. So plenty of time to see that. It'll be in the sky all winter long. Next slide probably is Jupiter. Yep. I just saw it driving into Boston tonight. So it's already up at 6:30 in the evening, -2.6, 45 arc second apparent diameter, January 10th opposition. And again, the challenge is, and I put the same, this is if we had a telescope outside right now, this is what Jupiter would look like. And there are the angular dimensions of the Galilean satellites. Do try to get out there and see them, and see if you can challenge yourself, up the power a little bit, see if you can actually pick up the discs. I mean, it's very doable, especially around opposition. A special treat towards the end of January will be a Callisto transit across the disk of the planet. Callisto is big and it's dark. It's got an albedo of something like 20%. So when it crosses the disk of the planet, it almost looks like a shadow, but it's not. You can actually see the planet transit, the moon transiting Jupiter. So that's coming up on like January 26th. I'll mention that next. All right, don't miss this planet. It's awesome. Our little box got shifted here, but our moon highlight of the month, see Mario Mata moon highlight of the month, is the crater Pleiades. Pleiades is this big impact crater right here. And it's quite near the crater Tycho, which is up that way. The slide got a little messed up. Relatively easy to see. It'll be best placed in the evening sky towards the end of the month. You need sort of a moon just past first quarter to actually pick it out. And it's a really nice crater to look at. Next slide, please.
Well, just jump before you do.
Oh, sure.
I always go back a second. I always get intrigued by this group of craters right here getting smaller as it goes around the kind of a semicircle there. That's an interesting feature inside.
And if you catch the crater right at sunrise, the lunar sunrise, these two craters here are the eyes of Pleiades. So their rims stick up out of the darkness and they look like two eyes staring at you. Next slide, please. I just wanted to point something out here. One of the things I like to look at, we can all see the big things on the moon, right? The big stuff is easy. The little stuff is more challenging. And so if you want to be challenged, sometimes they suggest this arc of craters is the real challenge, but the real challenge is this little cluster of craters right here. Those are only like a few miles across. And so see what your telescope can do. Pick a night when the seeing is good. Not that we get much of that in New England, but see if you can up the power and see if you can spot those little tiny craterlets on the floor of Pleiades. It's a great crater to look at. All right, next slide. What's next? There's an occultation of Lambda Aquarii on December 25th, the night, Christmas night, from about 7:06 to about 8:12. Those times depend on where you are located. All right, so get out there a few minutes early. That's a 3.7 magnitude star. That'll be a nice occultation, disappearing on the dark limb of the planet, of the moon. And so you can ink that one into your calendar. It's an M253 star, big star, 8.2 milliarc seconds, I think. I think it will still wink out instantaneously. 8.2 milliarc seconds isn't all that big. Anyway, that's coming up at the end of the month.
Is Santa's sleigh going to have any effect on this?
I'm sorry?
Santa's sleigh.
Oh, well, he'll be back at the North Pole by then. This is Christmas night. He'll be way done with his chores. Yeah, he's way done with his chores. All right, next slide. The fun double star of the month, I decided to pick 32 Eridani. I don't know how many people have seen this double star. It's kind of off the beaten path. but it's a really, really pretty double star to look at. We have a double star expert standing here tonight. What do you got to say about this star?
Nothing.
Nothing.
No, this is splittable with a little, I split it with a little 3-inch reflecting telescope at about 60 power. The thing is, with that small scope, I didn't notice any colors. I made a note that the primary star seemed whitish, but it's a G8 type star. And with larger telescopes, you should be able to see, I guess there's a lot of discussion, there's kind of like a topaz yellow and kind of a sea green. The thing is, it's an A-type star, which should really be white, but it's a contrast situation, just like Alberia. Sometimes the secondary star will have that bluish or greenish appearance. So it's a beautiful one to look at. So encourage you to go out and check it out. There's a couple of nice double stars in that constellation. 55 is another one that's good.
It's a little off the beaten path, but you can star hop to it pretty easily.
And the way things are going, double stars may be all we'll be able to look at in the future. So
that's right. Kelly, is this okay? Good. Is that better?
Yeah.
Good. Excellent. All right, next slide. The fun variable star of the month is.
withdraw the lawsuit.
Ben was the president. Just go. So, I'm not a big giant variable star guy. I mean, I like them when they're obvious, but one of my favorite variable stars is Omicron Ceti, Mira. And the reason I wanted to sort of remind you about that star this month is that it has a period of about 332 days. And this is the AAVSO chart of the last year. And you can see it peaked in sort of late February, early March. So 332 days puts it about right here in 2026. So if you start watching the star now, which is, pretty faint, way down here, this is, pretty close to today. You'll be able to watch that star rise up well into naked eye visibility as the months go by. It's just a fun star to watch. So I just wanted to remind you of that it's out there and it's going to reach a peak brightness sometime in early 2026.
And the AAB is so part of me. I've been a member for 40 years. That is a nice variable star, especially when it's bright. There have been occasions it's actually gotten as bright as almost first magnitude. And I remember one year, Mars was kind of fading away toward conjunction with the sun, while this one was at a maximum, and the two looked about the same. You could see the reddish color in this star. Yeah, Mario.
I think it's ruby red when it's dim. It turns a little more orangey when it's bright.
Yeah, they tend to, the fainter a variable star is, it's more intense. But this one was naked eye. You could see the reddishness of it when it was around. It was almost first magnitude.
If you want to see a great example of that, watch Arla Porus. That's a nice carbon star, a nice deep red carbon star. And when it's at its minimum brightness, which is around 11th magnitude, a little tough to find. It is so red. It's unbelievably red. The first night I went to look at it, I was using my 20-inch scope. I had to go in and get a finder chart and went, well, there it is, right in the field where I was looking at it. I couldn't even see it. It was so red and so faint that it barely registered, but it is a remarkably red star. So yeah, so you'll see that trend in especially in carbon stars. Let's not forget about T Corona Borealis. I mean, we've all sort of stopped thinking about that star because it's not in the evening sky anymore, but guess what, you guys? 80 years, 2026. Here we go. This could be the year that it comes up. And so let's keep our fingers crossed. It comes up relatively early in the morning now, 4:30ish. So while you're out looking at Mercury, just take your binoculars over and take a look to see if T Corona Borealis is behaving itself. Anyway, what else we got? What's next? The minimum Valgo. I'll just go through this super fast. You all know about that star and why it does its thing. There's a couple of convenient minima next Wednesday night and Saturday the 20th. So when you say it takes about 3 hours to do its thing.
Couple hours, yeah.
Yeah. So if you happen to be out, we can check that star out as well. All right, next slide. The Gemini meteor shower peaks this weekend. The moon doesn't come up till about 2 o'clock in the morning, so the sky should be relatively dark. And the radiant rises. I mean, it's pretty much at opposition, right? So the radiant comes up around sunset. You can look for long, graceful meteors. The Earth grazing meteors in the early evening. Geminids are particles of asteroid 3200 Phaethon. And sometimes the shower produces some very graceful, bright meteors. So it's worth getting out there. Bundle up. It's cold. Kelly, that would be something I would bundle up for on a night like tonight and go out, right? Just wear your long johns and get out there and look at it. It's a great meteor shower, and I highly recommend it. Next slide. All right,
All right,
yeah, I'll let
further
you
challenge.
talk for a while. I'm tired now.
Okay. Just a quick note about that, because I know you want to get going home. I've got to go home and take care of my wife. Yes.
Adrian's image.
Oh. You got them backwards?
No, this is the third month in a row we put the wrong name.
Third month in a row.
Oh, okay.
Changes.
That's Mario. Anyway, that was a tough one. Very few people saw that. The Observer's Challenge, by the way, kind of wound up this year. And it was started by Roger Ivester back in 2009. And we've decided to just start all over again because the club does seem to have a lot of interest in this. Wasn't too much follow-up on this because it's so far south. You're talking about 39 degrees south. And we had that one, there's another one. We'll go ahead to the next slide. Yeah, that's the legitimate one, right, Mario?
The one on the right is a combination of 3 different telescopes.
And this is with a C-Star S50. Again, look at what you can see with that particular scope. Next
I'm
slide.
impressed. And it's 50 to get that.
Yeah.
It took a lot of work to get the one on the right.
Well, he was in, I think he was on a Sky and Telescope trip to Chile, I think. Okay, we'll go to the next. The one this month, now we're going to go 125 degrees further north, just not too far from the North Star. This is NGC 188. It's a cluster. It's about 8 magnitude and about maybe 15 arc minutes across. It's very tough. It's a very faint object. We tried to see it with a 25-inch telescope last month, and we had a hard time. But you need to have absolutely clear skies.
When he says we had a hard time, we didn't see it.
Yeah, we couldn't see it at all. That doesn't mean I'm going to give up, though. It has been reported. Well, Steve O'Meara could see the Andromeda Galaxy by daylight, but he did see it with a 4-inch. And so did Sue French. So they reported seeing it with a small scope. I was going to try actually tonight before I left to come here, but not in this cold. But anyway, this one now, it's going to be kind of a tough object, but give that a try. That's our win for this month. We encourage you to go out, make some observations, written descriptions, send them in and we'll take it. We'll show you those observations next month. And finally, that means next slide. Now, this is one that Rich and I came up with. There was no object for January 2009, so we came up with the Messier 74 rather. And this is notorious because it's one of the toughest of the Messier objects to see. It was one of the last ones I did see it with that little 3-inch had been reflected, so it can be seen. But you need the dark skies again. This is very much like NGC 188. If there's any haze in the sky, forget about it. It's about 9.5 magnitude and maybe about 10 arc seconds. It's a spiral galaxy face on. And it's kind of like M33 and M101. It's the same type of thing.
It's actually pretty easy to get on the site for it.
Yeah, right near Pisces.
But seeing the galaxy is fairly challenging. And if you have any intention of doing a Messier marathon in March, this is usually the first one to fail on by March because it gets so low in the west. The Messier marathon depends on what weekend in March you want to play around. This is usually you fail the marathon right out of the gate because this one's so hard to find. So, you use this as a challenge object that is doable. It's actually a very doable challenge. And get yourself geared up for that, Messier marathon that you want to do. We wanted to go back to the 2009. I wrote them all out in a spreadsheet and looked for duplicates and took out the duplicates or the ones that we just did in the last year or two. And that's why we added this one here. That Glenn said Roger started that in February
2009. I think we're going to review them again.
M1, is that the next one?
I believe, that was your first one, was M1.
Another challenging object. That's not easy from in these light fluid skies. But on this one, we wanted to make it not impossible challenges like NGC 55. Did anybody see it? I didn't even try. When it transits, it's 8 degrees above our horizon in the south. 8 degrees.
Yeah.
It's like 2 fingers. That's it. You have to be like on the ocean if you have a horizon like that. It's crazy. So we're hoping that these challenges will be easier challenges to get more people out observing, and to have fun with this stuff, right? I mean, that's what we're here for, right? Anyway,
the last slide,
I think it is, except for this. Yeah, you want to get out of here, right?
I got to go take care of my wife. She's getting better, but it's been a very slow process. I just want to wish you all a Merry Christmas happy Hanukkah and clear skies in 2026. And keep looking up.
Thank you.
Thank you.
Well, so here are those were the dates that the clubhouse is officially open for December, January, and February. Please come and visit us. You know, sometimes the field gets a little snowy in the winter time, but we try to keep the observatories open and come on out and have some fun out there.
Weather's looking decent for tomorrow.
There you go. Tomorrow night's looking pretty okay.
That is the close of our meeting, and our speaker next month is from Sky and Telescope and Sean Walker. See you there. Thank you.